What drives the universe? What invisible forces shape its evolution, pulling and pushing galaxies across vast expanses of time and space? In the early 1990s, these profound questions spurred two groundbreaking scientific endeavors, the High-Z Supernova Search Team and the Supernova Cosmology Project. These international collaborations united astronomers from around the globe to pursue a common goal: to unravel the mystery of the universe's expansion and its underlying composition. The prevailing theory at the time posited that the universe's expansion, set into motion by the Big Bang, was gradually decelerating under the influence of gravity. All matter and radiation, it was believed, exerted a gravitational pull that acted as a cosmic brake. By measuring this deceleration, astronomers hoped to gain a deeper understanding of the total matter and energy that constituted the universe. The promise of such knowledge compelled the teams to employ the mightiest telescopes of their era, including the 8-meter Keck telescope in Hawaii and the Hubble Space Telescope, whose orbit around Earth provided unparalleled clarity. The astronomers focused their efforts on Type Ia supernovae, cataclysmic stellar explosions so luminous that they could be observed across billions of light-years. These explosions served as standard candles, objects whose intrinsic brightness is well known, enabling precise measurements of their distance and the rate of cosmic expansion at the time their light began its journey to Earth. These supernovae, scattered across the far reaches of the universe, became the key to unlocking the history of the cosmos. Initially, the teams anticipated results that would align with established expectations, evidence of a universe whose expansion was steadily slowing under the influence of gravity. But as their data poured in, a startling pattern emerged. The universe was not decelerating. It was accelerating. Galaxies were moving away from one another at ever-increasing speeds, as though propelled by an unseen and mysterious force. This revelation was as unexpected as it was perplexing. The researchers meticulously rechecked their data, scrutinizing every observation and calculation. Could there have been an error in their methods? Was an unknown phenomenon skewing their results? Yet, time and again, the data confirmed the same conclusion: the expansion of the universe was accelerating. This realization defied the conventional understanding of gravity and demanded a radical new explanation. To account for this acceleration, the teams proposed the existence of a previously unknown and pervasive component of the cosmos, dark energy. Unlike anything previously theorized, dark energy was an invisible and intangible force that permeated the entirety of space, driving the accelerated expansion of the universe. Its properties were baffling. It neither emitted or absorbed light and remained undetectable by any instrument available to science. Yet its influence was undeniable. This groundbreaking discovery earned the leaders of the two teams, Brian Schmidt, Saul Perlmutter, and Adam Rees, the 2011 Nobel Prize in Physics. Their work revealed a universe that was far stranger and more complex than previously imagined. Dark energy, it turned out, was not a minor player in the cosmic drama. It accounted for an astonishing 68% of the universe's total energy density. Together with dark matter, which made up another 27%, these unseen components dwarfed the ordinary matter, the atoms that compose stars, planets, and all visible structures, which constituted a mere 5% of the cosmos. This discovery marked a turning point in the field of cosmology, concluding a century of transformative insights into the nature of the universe. The early 20th century had already shattered humanity's geocentric illusions, revealing our sun as an ordinary star in an unremarkable galaxy, adrift in an expanding universe. By mid-century, the realization that most of the universe's matter was invisible and detectable only through its gravitational effects had further deepened the mystery of the cosmos. But the discovery of dark energy eclipsed all that had come before, introducing an entirely new and confounding element to the equation. Dark energy's implications extend beyond its role in cosmic acceleration. It challenges fundamental theories of physics, including Einstein's general relativity, and raises profound questions about the nature and fate of the universe. Some scientists speculate that dark energy might be an intrinsic property of space itself, linked to the vacuum energy predicted by quantum mechanics. Others propose that it points to new and uncharted realms of physics, possibly involving forces or dimensions beyond our current understanding. On May 29, 1919, a total eclipse of the Sun swept across the southern Atlantic, offering a rare opportunity to test Einstein's revolutionary general theory of relativity. British astronomers Arthur Eddington and Frank Dyson organized 2 expeditions to observe this phenomenon. One team traveled to Sobral, Brazil, while the other set up camp on the island of Principe off the coast of West Africa. Their goal was audacious: to photograph background stars during the eclipse and measure the subtle deflection of their light caused by the Sun's gravity. This effect, known as gravitational lensing, was a cornerstone prediction of Einstein's theory. The challenges were immense. On Principe, Eddington endured relentless rain and heavy cloud cover, with the sun only breaking through moments before the eclipse. Amid the fleeting clear skies, Eddington worked frantically, changing photographic plates and capturing the critical data. When the plates were analyzed, the results were unequivocal. The background stars had shifted by the precise amount predicted by Einstein. Gravity, as described by general relativity, was not a simple force but a curvature of space-time itself. The news reverberated around the world, and Einstein became an icon, his theory validated under the skies of Africa and Brazil. Yet, Einstein himself believed gravitational lensing had little practical application. He considered stars too small to produce significant effects, rendering the phenomenon more a theoretical curiosity than a tool for discovery. However, this view would be upended within decades by a chain of remarkable findings. In the 1930s, Fritz Zwicky, a brilliant and iconoclastic astronomer at Caltech, made an observation that would lay the groundwork for modern cosmology. Studying the Coma Cluster, a colossal congregation of galaxies 300 million light-years away, Zwicky applied a novel method to weigh the cluster. By measuring the velocities of the galaxies within it, he calculated the gravitational pull required to keep the cluster intact. His findings were startling. The visible matter in the galaxies was insufficient to account for their observed speeds. The cluster should have flown apart under its own motion. Zwicky concluded that an unseen dunkle materie, dark matter, must be providing the additional gravity needed to bind the cluster. Though revolutionary, Zwicky's discovery was largely ignored at the time, partly due to his abrasive personality. His notion of dark matter languished in obscurity, overshadowed by other pressing questions in astronomy. It wasn't until the 1970s that dark matter would re-emerge as a central mystery of the cosmos, thanks to the meticulous work of Vera Rubin. Rubin, a pioneering astronomer who overcame significant gender barriers, turned her attention to spiral galaxies like the Milky Way. Collaborating with Kent Ford, she measured the rotation curves of stars within these galaxies. According to Newtonian mechanics, stars at the outskirts of a galaxy should orbit more slowly, as gravity weakens with distance from the galactic center. Instead, Rubin found that the outer stars maintained a nearly constant speed, defying expectations. The explanation was inescapable. Vast amounts of unseen dark matter were providing the additional gravitational pull needed to sustain these high velocities. Rubin's findings revitalized interest in Zwicky's dark matter, and astronomers began to uncover its fingerprints across the universe. One of the most compelling tools in this investigation was gravitational lensing, the very phenomenon Einstein had deemed impractical. Zwicky himself had speculated that massive galaxy clusters could act as cosmic lenses, bending and magnifying the light of distant objects. However, it wasn't until the 1960s and 1970s, with the discovery of quasars, that this idea was fully realized. Quasars, among the brightest objects in the universe, are powered by supermassive black holes at the centers of galaxies. Their immense luminosity made them visible across billions of light-years, providing ideal targets for gravitational lensing studies. In 1979, astronomers identified an intriguing quasar, designated Q0957+561, that appeared to have a twin. Careful analysis revealed that the twin was not a separate object but a duplicate image caused by the gravitational lensing of a massive galaxy lying between the quasar and Earth. Einstein's theoretical prediction had found a powerful real-world application. Gravitational lensing has since become one of the most vital tools in modern astronomy. Clusters of galaxies, laden with dark matter, act as natural telescopes, magnifying distant galaxies and revealing structures that would otherwise be too faint to detect. These gravitational lenses produce stunning arcs and distortions, each a testament to the hidden mass shaping the universe. Every instance of gravitational lensing tells the same story. The visible stars and gas in the universe are merely the tip of the iceberg. The majority of the mass in the cosmos is dark, invisible to telescopes yet fundamental to the universe's structure. Beyond lensing, dark matter's presence is inferred from galaxy rotation curves, the motions of galaxy clusters, and even the large-scale flows of galaxies across the cosmos. For millennia, humans have gazed at the night sky, drawing constellations and ascribing meaning to the arrangements of stars. Yet beyond these simple patterns lie incomprehensibly vast structures, galaxy clusters stretching billions of light-years across, interwoven by filaments and separated by immense voids. Names like the Great Wall, the Giant Arc, and Laniakea have been given to these colossal formations, but their origins remained a mystery until the late 20th century. In the 1970s, astronomers began the ambitious task of mapping the locations of galaxies to understand the large-scale structure of the universe. By measuring the light from individual galaxies, they could calculate their redshifts, a proxy for distance based on the universe's expansion. This painstaking work led to the creation of the first cosmic atlases. Early efforts, such as the CFA Redshift Survey based at Harvard University's Center for Astrophysics, charted galaxy positions across the sky. The data revealed that galaxies were not randomly distributed but instead formed a vast cosmic web. Clusters of galaxies were connected by filaments, and between these structures lay enormous voids, giving the universe a sponge-like appearance. By the mid-1990s, astronomers John Huckra and Margaret Geller had mapped the positions of 18,000 galaxies. Their work uncovered immense formations like the Great Wall and the Stickman, each composed of thousands of galaxies. More advanced surveys, such as the 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey, have since mapped millions of galaxies, providing an even clearer view of the universe's large-scale architecture. But the discovery of this cosmic web raised a profound question: where did this intricate structure come from? The fiery birth of the universe in the Big Bang left it featureless, with hydrogen and helium evenly distributed throughout. What transformed this smooth primordial state into the complex cosmos we see today? The answer lies in the invisible scaffolding provided by dark matter. In the earliest moments of the universe, a rapid burst of expansion known as inflation introduced tiny ripples in the density of matter. These ripples were minute, but they provided the seeds for gravity to act upon. Slightly denser regions began to draw in matter from their surroundings, creating pockets of higher density. This process marked the beginning of cosmic structure. As gravity continued its work, hydrogen and helium gas pooled into these dense regions. Over the course of 100 million years, these pockets of matter grew, fragmenting into clouds that cooled and collapsed. Within these clouds, the first stars ignited, bringing light to the cosmos. These infant stars clustered together to form the first galaxies, lighting up the dense knots of dark matter where they formed. Over billions of years, dark matter continued to draw in mass, accompanied by growing quantities of gas and stars. This process gave rise to the fully formed galaxies we see today, nestled within immense halos of dark matter. Without the gravitational framework provided by dark matter, the formation of galaxies would have been exceedingly difficult, if not impossible. Understanding galaxy evolution is an intricate task. Astronomers must account for the behavior of gas, the life cycles of stars, and the influence of black holes, all of which interact in highly complex ways. To untangle these processes, researchers rely on supercomputers to simulate the universe's evolution. These simulations allow scientists to observe the interplay of forces shaping the cosmos, offering breathtaking insights into how galaxies emerge from the early universe's fog. One crucial revelation from these simulations is the role of dark matter's properties in forming cosmic structures. For galaxies to coalesce, dark matter must move relatively slowly, allowing it to clump together rather than dispersing. This behavior led to the designation of cold dark matter, with cold referring to its sluggish motion. Dark matter, then, is not just a passive background element but the great sculptor of the universe. It provided the gravitational framework upon which galaxies and stars could evolve, shaping the complexity of the cosmos. Yet, for all its importance, dark matter remains one of the greatest mysteries of modern science. What is it made of? How does it interact with ordinary matter? And why does it exist at all? From hypothesized particles to ancient astronomical phenomena, the quest to understand dark matter has uncovered tantalizing clues but also deepened the mystery. In the 1930s, Wolfgang Pauli faced a puzzling problem in particle physics. Beta decay, a well-studied process where an atomic nucleus emits an electron or its antimatter counterpart, seemed to violate the conservation of energy. Identical atomic nuclei, undergoing the same decay process, ejected particles with varying speeds and energies. This inconsistency suggested that energy was inexplicably disappearing, a conclusion Pauli found intolerable. Instead, he proposed the existence of an invisible particle, the neutrino, that carried away the missing energy. This hypothetical particle had peculiar properties. Unlike photons, which interact readily with matter, neutrinos scarcely interacted with atoms at all. For decades, neutrinos remained purely theoretical, until sensitive experiments near nuclear reactors finally detected them in the 1950s. Astronomers soon realized that neutrinos were abundant, generated in nuclear reactions during the universe's earliest moments. For a time, they were considered a candidate for dark matter. However, experiments revealed that neutrinos were too light and fast-moving to account for the gravitational effects attributed to dark matter. The search continued. What could be dark enough and massive enough to account for dark matter's gravitational influence? One possibility was atomic matter, chilled clouds of hydrogen, too cold to emit light. However, the Big Bang's elemental cooking placed strict limits on the amount of atomic matter in the universe, and it fell far short of the mass needed. Black holes, the ultimate traps for light, seemed another viable candidate. Some physicists hypothesized that primordial black holes, formed in the chaotic first moments of the Big Bang, might populate the cosmos in vast numbers. These black holes, however, would betray their presence through gravitational lensing, magnifying distant starlight as they passed in front of it. In the 1990s, after years of searching for such events, astronomers found no evidence to support this theory. Black holes, too, were ruled out. Meanwhile, particle physicists turned their attention to the subatomic realm. The 20th century had been a golden age for particle physics, culminating in the Standard Model, a comprehensive framework describing the fundamental particles and forces of nature. The Standard Model successfully accounted for the electromagnetic, strong, and weak forces but remained incomplete. Gravity, the most familiar force, resisted incorporation into the quantum framework. Moreover, dark matter was conspicuously absent from this elegant mathematical structure. Physicists saw this incompleteness as an opportunity. Extending the Standard Model's mathematics could reveal new particles, some of which might be candidates for dark matter. One promising idea emerged in the 1970s to address a peculiar issue with the strong nuclear force. The equations governing this force allowed for a symmetry-breaking phenomenon known as charge parity, CP, violation. However, no experiment had observed CP violation in the strong force, suggesting the need for an additional mechanism to preserve symmetry. The Pecky-Iquin mechanism, introduced to resolve this issue, implied the existence of a new particle, the axion. This hypothetical particle, named whimsically after a detergent for its ability to clean up theoretical problems, had characteristics that made it a compelling dark matter candidate. Axions were light, interacted minimally with other matter, and could exist in vast numbers. Yet, despite extensive searches, axions remain undetected. Other extensions to the Standard Model have yielded a menagerie of dark matter candidates. Supersymmetry, a theoretical framework doubling the known particle family, introduced possibilities such as photinos and neutralinos, which might account for dark matter. Additional candidates, including sterile neutrinos, WIMPs, weakly interacting massive particles, and more exotic options like Q-balls and asymmetric dark matter, have been proposed. However, no experiment or observation has definitively pointed to any of these candidates, leaving the mystery unsolved. To bridge the gap between theory and observation, some physicists and astronomers have collaborated to search for indirect evidence of dark matter. Many theoretical models suggest that dark matter particles could self-annihilate, much like electrons and positrons, releasing high-energy radiation in the process. Telescopes have been trained on regions with dense concentrations of dark matter, such as the galactic center, in search of gamma-ray emissions. Intriguingly, a faint glow of gamma rays has been detected in these regions, but its origin remains uncertain. It could be the long-sought signal of dark matter, or it might arise from more mundane astrophysical phenomena. Further observations will be needed to unravel this ambiguity. By the late 1990s, significant progress had been made. Physicists had narrowed the field of possibilities, and astronomers had refined their tools for studying the cosmos. Yet, as often happens in science, a new discovery was about to overturn prior assumptions and introduce an even greater puzzle. The search for dark matter was far from over, but each step brought us closer to understanding the unseen forces shaping our universe. What is this mysterious force that drives the universe to expand ever faster? Why does the cosmos appear dominated by something so elusive, yet so pervasive? These questions lie at the heart of modern physics, challenging our understanding of the universe and forcing us to rethink its fundamental nature. The story of dark energy is both ancient and cutting-edge, a tale that intertwines the theories of Einstein with the latest observations of modern astronomy. The seeds of this mystery were sown over a century ago, when Albert Einstein formulated his general theory of relativity. This revolutionary framework described gravity not as a force, but as the curvature of spacetime caused by mass and energy. Armed with these equations, Einstein turned his attention to the cosmos, seeking to describe its large-scale behavior. Yet his equations revealed an unsettling prediction: the universe should be dynamic, either expanding or contracting. Einstein, however, believed in a static, eternal universe, unchanging across time. To reconcile his equations with his philosophical preference, Einstein introduced the cosmological constant, a term that acted as a repulsive force, counterbalancing gravity to produce a stable, static universe. This adjustment satisfied Einstein, but not everyone agreed. Russian physicist Alexander Friedmann revisited Einstein's equations and demonstrated that an expanding universe was a more natural outcome. Initially dismissive, Einstein eventually conceded, abandoning the cosmological constant and famously calling it his biggest blunder. For decades, the concept lay dormant. Meanwhile, observational astronomy was forging ahead. At Mount Wilson Observatory, Edwin Hubble used the 100-inch Hooker telescope, the largest of its time, to measure distances to galaxies. By identifying Cepheid variable stars within these galaxies, Hubble calculated their true brightness and determined their distances. Combining these measurements with galactic velocities obtained through Doppler shifts, Hubble uncovered a remarkable relationship: the farther a galaxy, the faster it was receding. This discovery provided conclusive proof that the universe was expanding, a revelation that reshaped cosmology. Over the ensuing decades, astronomers refined Hubble's work, conducting vast surveys to measure galactic distances and velocities. These efforts culminated in the determination of Hubble's constant, quantifying the rate of cosmic expansion. Yet by the late 20th century, a new chapter was unfolding. Observations of distant supernovae, used as precise standard candles, revealed a surprising result: the expansion of the universe was not slowing down as expected, but accelerating. This discovery pointed to the existence of a mysterious force counteracting gravity and driving galaxies apart at increasing speeds. Astronomers named this enigmatic phenomenon dark energy. Yet its theoretical foundation was far from new. The accelerating expansion could be explained by reinstating Einstein's discarded cosmological constant, giving the term new life as the leading explanation for dark energy. The implications were staggering. Cosmic accounting revealed that ordinary atomic matter, the stars, planets, gas clouds, and galaxies that compose the visible universe, constituted less than 5% of the total. Dark matter, the unseen scaffolding holding galaxies together, made up roughly 25%. Dark energy dominated the remainder, accounting for a stunning 70% of the universe's energy density. This revelation raised profound questions. Why is the universe so overwhelmingly dominated by this mysterious force? And what is its true nature? One of dark energy's most perplexing properties is its constancy. As the universe expands, matter and radiation thin out, yet dark energy's density appears to remain unchanged. In the early universe, matter and radiation were dense, and dark energy's influence was negligible. However, as the cosmos expanded and matter thinned, dark energy began to dominate. About 5 billion years ago, this tipping point was reached, marking the onset of accelerated expansion. This acceleration has profound consequences for the universe's future. As dark energy continues to dominate, galaxies will be driven farther apart at increasing speeds. In approximately 100 billion years, galaxies beyond our local group will have receded beyond the cosmic horizon, becoming permanently inaccessible. The night sky, once teeming with the light of distant galaxies, will fade into darkness. The universe will become an isolated, empty expanse, shaped and defined by the relentless influence of dark energy. The evidence for dark energy's existence is overwhelming. It is imprinted in the large-scale distribution of galaxies, the cosmic microwave background radiation, a relic of the Big Bang, and the accelerating expansion of spacetime itself. Yet its nature remains one of the greatest enigmas in science. Is it a fundamental property of spacetime, as Einstein's cosmological constant suggests? Or does it hint at new physics beyond our current understanding? As researchers continue to probe these questions, dark energy stands as both a testament to the mysteries of the cosmos and a challenge to our ingenuity in uncovering its secrets. To understand dark energy, we must delve into the quantum nature of the vacuum, the limits of current physics, and the vast theoretical playgrounds that attempt to explain its enigmatic properties. In quantum mechanics, empty space is never truly empty. According to Heisenberg's uncertainty principle, energy can fluctuate in and out of existence on extremely small timescales. These quantum fluctuations imbue the vacuum with a kind of tension, a property that can even be measured in experiments. This vacuum energy is one of the potential explanations for dark energy, but significant problems arise when attempting to quantify it. When physicists calculate the energy density of the vacuum, the results are absurd. The predicted value is larger than the observed amount of dark energy by a staggering factor of 10 to the power of 120. This discrepancy has been called the worst prediction in the history of physics, underscoring how little we truly understand about the quantum vacuum. If dark energy is indeed linked to the vacuum, it suggests we are missing a fundamental aspect of its behavior and properties. This vacuum energy hypothesis is just one among many. With so little observational evidence to constrain theories, the nature of dark energy has become a fertile ground for speculation. Some propose fields that operate in the background of the universe, influencing its expansion. Others draw connections to the epoch of inflation, an explosive period of accelerated expansion thought to have occurred when the universe was just 10 to the power of -35 seconds old. Inflation itself was driven by a hypothetical field known as the inflaton. Could dark energy be a resurgence of this primordial force? The answer, at best, is a tentative maybe. Another intriguing possibility is that dark energy and dark matter, the two dominant dark components of the universe, might share a common origin. Some mathematical models propose interactions within a dark sector, a realm of physics as rich and complex as the atomic world but hidden from direct observation. Such a sector could provide the key to unifying our understanding of these mysterious forces. However, without clear observational evidence, these ideas remain speculative. To break this impasse, astronomers and physicists are designing increasingly ambitious experiments. Cutting-edge telescopes, such as the Vera Rubin Observatory's 8.4-meter telescope and the European Extremely Large Telescope, aim to uncover new clues about dark energy. These instruments will probe whether dark energy is truly Einstein's cosmological constant, a fixed and unchanging property of space, or if it evolves over time, potentially decaying into matter and radiation. Such findings could revolutionize our understanding of the universe. Yet, current observations consistently suggest that dark energy behaves precisely as Einstein's cosmological constant predicts. This constancy is both reassuring and unsettling. If dark energy is indeed an unchanging property of space, it might be fundamentally unknowable, a basic feature of the universe with no deeper explanation. For some cosmologists, this prospect is deeply unsatisfying, representing a potential failure to uncover the universe's underlying laws. An alternative explanation posits that our theories of gravity are incomplete. Perhaps Einstein's general relativity, while remarkably successful, is only an approximation of a deeper truth. If gravity behaves differently on cosmic scales, it could account for the observed phenomena of dark matter and dark energy without requiring them to exist as physical entities. However, no modified theory of gravity has yet matched Einstein's in both elegance and predictive power. As things stand, the universe remains dominated by its dark side. Dark energy and dark matter govern its structure, evolution, and ultimate fate, yet their true nature eludes us. If they are physical substances, understanding their properties will be essential to answering fundamental questions about cosmic history and the laws of physics. If they are mirages arising from the limitations of our theories, their resolution will demand a complete overhaul of our understanding of the universe. Until these mysteries are unraveled, the dark side of the universe holds the keys to its secrets, and it guards them tightly. For now, we can only explore, theorize, and observe, ever striving to illuminate the darkness that surrounds us. What drives humanity to measure the world in extremes? Why are we so captivated by the fastest, the largest, the most powerful? This obsession with superlatives reflects our unending curiosity about the limits of nature, and it is through such pursuits that we have shaped and reshaped the course of history. Yet, in our quest for the ultimate, we have also created some of the most destructive forces imaginable. One such example is the Tsar Bomba, a testament to both human ingenuity and hubris. But even this colossal explosion pales in comparison to the forces at work in the wider cosmos. Let us embark on a journey from the depths of human ambition to the incomprehensible scale of stellar cataclysms, all bound by the enigmatic force of gravity. On October 30, 1961, a Tupolev Tu-95V bomber flew over Novaya Zemlya, an archipelago in the Arctic Ocean. Its mission was unprecedented, to unleash the most powerful man-made explosion in history. Suspended beneath parachutes to delay its descent, a 27-ton bomb nicknamed the Tsar Bomba fell gracefully toward the Earth. The delay was essential, giving the bomber time to escape the ensuing cataclysm. When the bomb detonated, it released a staggering energy equivalent to 50 megatons of TNT, 3,800 times more powerful than the bomb dropped on Hiroshima. The mushroom cloud soared 60 kilometers into the sky, and the flash was visible over 1,000 kilometers away. Heat from the blast caused third-degree burns to those within a 100-kilometer radius. This unparalleled display of power was both a political statement and a sobering reminder of humanity's destructive capabilities. However, in the same year, the cosmos unveiled a spectacle that dwarfed even the mightiest human invention. Astronomers observed the death of a star in a galaxy 45 million light-years away. This was a supernova, an event triggered when a massive star exhausts its nuclear fuel and collapses under its own gravity. With its core unable to resist the inward pull, the star implodes at a fraction of the speed of light, causing temperatures to soar and resulting in an explosion that scatters stellar material across light-years of space. The energy released by this single event is beyond comprehension, outshining entire galaxies. Yet, even the grandeur of a supernova is overshadowed by an even rarer phenomenon, the hypernova. These extraordinary explosions occur when stars more than 30 times the mass of our Sun meet their end. The star's core collapses to form a black hole, and the remaining stellar material ignites under the influence of extreme gravitational forces and searing winds of nickel-rich radiation. Hypernovae are up to 100 times more powerful than supernovae, representing the pinnacle of cosmic violence. They are the most energetic events in the observable universe, fueled by gravity's relentless pull. Despite the seemingly boundless power of these stellar events, gravity's influence is surprisingly weak when measured against the universe's other fundamental forces. There are four such forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. The strong nuclear force binds protons and neutrons within atomic nuclei, making it the strongest of the four. The electromagnetic force governs interactions between charged particles and enables the radiation that lights and warms our universe. Even the weak nuclear force, which facilitates radioactive decay and stellar fusion, vastly outmatches gravity. In fact, gravity is weaker than the weak force by a factor of 10 to the 25th power, 10 trillion times. This apparent weakness poses a profound mystery, known as the hierarchy problem. How can gravity, so feeble at atomic scales, dominate the universe at large? To feel its effects, we require enormous accumulations of matter, such as planets, stars, and black holes. A simple ant, using the chemical energy in its legs, can defy the gravitational pull of an entire planet. Yet, when matter aggregates on a cosmic scale, gravity shapes the structure of galaxies, governs the orbits of celestial bodies, and even dictates the flow of time itself. The enigma of gravity's weakness has led physicists to propose extraordinary explanations. Some theories suggest that gravity's effects are diluted because it extends into dimensions beyond the familiar three of space and one of time. These additional dimensions, if they exist, could hold the key to understanding gravity's place among the fundamental forces. To unravel these mysteries, we must look to the earliest moments of the universe. In the seconds following the Big Bang, the fundamental forces were unified. As the universe expanded and cooled, they separated, a process that shaped the cosmos as we know it. The study of this period could provide insights into the origins of gravity and its apparent disparity with the other forces. Moreover, experiments at the frontiers of particle physics, such as those conducted at the Large Hadron Collider, aim to probe the nature of gravity and its relationship to the quantum realm. These investigations may uncover evidence of extra dimensions or reveal particles associated with gravity, known as gravitons. Such discoveries would revolutionize our understanding of the universe's fundamental structure. The quest to understand gravity is not merely an academic pursuit. It is a journey that touches on the very fabric of existence, from the smallest particles to the largest galaxies. Gravity shapes our daily lives, keeps our feet on the ground, and challenges our engineers as they reach for the stars. It binds the universe together, yet its true nature remains elusive. As we gaze upon the remnants of supernovae and hypernovae, and as we study the colossal black holes at the hearts of galaxies, we are reminded of gravity's dual nature, at once unimaginably powerful and deceptively weak. It is a force that defines the cosmos yet humbles us with its mysteries. To truly understand it, we must look beyond our own world, to the distant stars and the origins of time itself. Only then can we hope to grasp the full scope of this most fundamental of forces. Why do we fall? Gravity, the first of nature's forces to be recognized and quantified by science, is both the most familiar and the most enigmatic. For all its universality, gravity continues to defy complete understanding, eluding the grasp of even the most brilliant minds in history. To unravel its mysteries is to embark on a journey through the centuries, from the orchards of 17th century England to the curved geometries of spacetime, and onward to the frontiers of modern physics. The tale begins, as so many scientific odysseys do, with Isaac Newton. A solitary and meticulous man, Newton was as reserved in his personal life as he was prolific in his intellectual pursuits. The legend of his epiphany beneath an apple tree has become as much a part of scientific folklore as gravity itself. Whether or not an apple ever truly struck the ground before his contemplative eyes, the story captures the essence of Newton's genius, his ability to see the profound in the mundane. In 1666, during a plague-induced closure of Cambridge University, Newton retreated to his family home in Lincolnshire. There, in the quiet isolation of Woolsthorpe Manor, he laid the groundwork for his theory of universal gravitation. Why should that apple always descend perpendicularly to the ground, he wondered, as he later recounted. This simple question led him to imagine an invisible force extending beyond the Earth's surface, reaching across the heavens to bind the moon in its orbit and guide the planets on their celestial paths. Newton's formulation was elegantly simple. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This universal law of gravitation proved astonishingly effective. It explained the motions of the planets, the behavior of tides, and even the trajectories of comets. Yet, for all its predictive power, Newton's theory left unanswered the fundamental question: what is gravity? Newton himself was acutely aware of this limitation. That gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it, he wrote. While his equations worked, he could not fathom how one object could exert a force on another across empty space. Newton's reluctance to ascribe an intrinsic nature to gravity reflected his scientific humility and presaged the challenges that would confront physicists in the centuries to follow. For 200 years, Newton's theory reigned supreme. It guided explorers across uncharted oceans, enabled the construction of mechanical wonders, and illuminated the dance of celestial bodies. Yet, as observational techniques grew more sophisticated, cracks began to appear in its foundation. The orbit of Mercury, for instance, deviated ever so slightly from Newtonian predictions. This wobble, or precession, hinted at forces beyond the scope of classical mechanics. The turn of the 20th century brought with it a revolution in physics. Albert Einstein, a German-born physicist with an uncanny ability to see the universe in ways no one else could, turned his attention to the shortcomings of Newtonian gravity. Building on the insights of special relativity, Einstein proposed a radical new framework, general relativity. At its core was a simple yet profound idea: gravity is not a force in the traditional sense, but a manifestation of the curvature of spacetime. To grasp this concept, imagine a heavy object placed on a taut rubber sheet. The weight of the object distorts the sheet, creating a depression. Smaller objects placed on the sheet will naturally roll toward the center of the depression, not because they are being pulled, but because they are following the contours of the curved surface. Similarly, Einstein argued, massive objects like stars and planets warp the fabric of spacetime, and it is this curvature that guides the motion of objects within it. Einstein's theory was as mathematically intricate as it was conceptually revolutionary. It predicted phenomena that Newtonian gravity could not explain, such as the bending of light around massive objects and the precise precession of Mercury's orbit. These predictions were spectacularly confirmed during a solar eclipse in 1919, when astronomers observed starlight curving around the Sun exactly as Einstein had calculated. General relativity not only supplanted Newtonian mechanics but also opened the door to a universe far stranger than anyone had imagined. Yet, for all its triumphs, general relativity left its own set of mysteries in its wake. While it described the behavior of gravity on cosmic scales with unparalleled precision, it offered little insight into its origins. Why does gravity exist? Why is it so weak compared to the other fundamental forces? And how does it reconcile with the quantum realm, where the rules of physics take on an entirely different form? The weakness of gravity is one of the most perplexing puzzles in physics. Compared to the strong nuclear force, which binds protons and neutrons within atomic nuclei, gravity is astonishingly feeble. To put it in perspective, the electromagnetic force between two electrons is about 10 to the power of 36 times stronger than the gravitational attraction between them. This disparity, known as the hierarchy problem, suggests that we are missing a crucial piece of the puzzle. One possibility is that gravity operates on a fundamentally different plane than the other forces. Some physicists speculate that it may leak into extra dimensions beyond the familiar three of space and one of time. These hypothetical dimensions, though hidden from everyday experience, could dilute gravity's effects in our observable universe. Experiments at facilities like the Large Hadron Collider are probing these ideas, searching for evidence of gravitons, theoretical particles associated with gravity, or subtle deviations from the inverse square law at microscopic scales. Another avenue of exploration lies in the early universe. In the moments following the Big Bang, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are believed to have been unified. As the universe expanded and cooled, they separated, each taking on its distinct characteristics. Understanding this process could shed light on gravity's true nature and its role in the cosmos. Despite decades of effort, the quest to unify general relativity with quantum mechanics remains one of the greatest challenges in theoretical physics. The two frameworks are mathematically incompatible, yet both are essential for describing the universe. While general relativity governs the behavior of massive objects and the structure of spacetime, quantum mechanics dictates the interactions of particles on the smallest scales. Bridging this divide may require a paradigm shift as profound as Einstein's reconceptualization of gravity a century ago. One promising candidate for such a unifying theory is string theory, which posits that all particles are not point-like but rather tiny vibrating strings. These strings exist in a multidimensional spacetime, and their vibrations give rise to the fundamental forces and particles we observe. String theory suggests that gravity arises naturally within this framework, offering a tantalizing glimpse of how the quantum and cosmic realms might be reconciled. However, it remains a deeply mathematical and experimentally unverified construct, as elusive as the nature of gravity itself. In the meantime, gravity continues to humble and inspire us. It shapes the galaxies, governs the orbits of planets, and choreographs the intricate ballet of celestial bodies. It binds us to the earth, enabling the simplest pleasures of walking and running, and challenges us to reach for the stars. From the fall of an apple to the bending of starlight, gravity's story is one of discovery and wonder, a testament to humanity's enduring curiosity about the universe. As we stand on the precipice of new discoveries, the questions that Newton and Einstein grappled with remain as relevant as ever. Why do we fall? What is the nature of the force that binds the cosmos together? To seek these answers is to confront the very fabric of reality, to delve into the origins of existence, and to marvel at the profound simplicity and complexity of the universe. Gravity, the silent architect of the cosmos, awaits our understanding, a challenge that beckons us to explore, to question, and to dream. Ripples from the beginning of time. To detect ripples in the very fabric of space that have traveled across the cosmos for billions of years? Such questions evoke a profound sense of wonder, pushing the boundaries of our imagination as we attempt to understand the origins of our universe. These ripples, gravitational waves, carry whispers from the birth of the cosmos, offering us glimpses into epochs long before stars and galaxies existed. To follow their journey is to trace the history of existence itself, from cataclysmic collisions to the enigmatic beginnings of spacetime. A billion years ago, the Earth was a quiet, unchanging world. The planet languished in a geological and evolutionary stasis that scientists call the boring billion. Life, once brimming with innovation, had stalled. The planet's chemistry, climate, and geography appeared frozen, offering no clue of the monumental cosmic events occurring far beyond Earth's skies. In a distant region of the universe, two black holes, each over 30 times the mass of our Sun, were locked in an inexorable dance. Spinning ever faster, their violent embrace culminated in a collision so powerful it sent ripples through spacetime itself. These gravitational waves raced outward at the speed of light, carrying with them the energy of a cataclysm whose magnitude defies comprehension. But for over a billion years, these ripples passed unnoticed through the universe. Their arrival on Earth came not during the boring billion but in an age of human ingenuity. On September 14, 2015, a revolutionary instrument known as LIGO, Laser Interferometer Gravitational Wave Observatory, detected these waves. Just 2 days after being activated, LIGO recorded a fleeting signal, a chirp lasting less than a fifth of a second. This signal was the faint echo of the black hole collision, reaching Earth after a journey of cosmic proportions. LIGO's achievement was nothing short of extraordinary. For decades, skeptics doubted whether gravitational waves, predicted by Einstein's general theory of relativity in 1915, could ever be detected. Einstein himself was unsure if such waves, distortions in spacetime caused by massive gravitational disturbances, would be measurable. LIGO overcame these doubts by using lasers to detect minute changes in the lengths of its arms, changes smaller than the width of a proton. When a gravitational wave passed through the observatory, it subtly altered the distance between mirrors placed kilometers apart, producing the unmistakable chirp that heralded the arrival of waves from a billion-year-old event. This discovery was not just a technical triumph, it was a new way of observing the universe. For centuries, astronomers relied on light, visible, infrared, and other wavelengths to study the cosmos. But light can be obscured or absorbed, limiting our view of the universe's most extreme events. Gravitational waves, however, penetrate all matter unimpeded, carrying information from the darkest and most distant corners of existence. LIGO's detection opened a new window on the cosmos, allowing scientists to hear the universe for the first time. Subsequent discoveries confirmed the power of this new tool. In 2017, LIGO detected gravitational waves from a pair of merging neutron stars. This event produced not only gravitational waves but also gamma rays and visible light, enabling astronomers to observe it across multiple wavelengths. Such multi-messenger astronomy confirmed the violent origins of heavy elements like gold and platinum, forged in the aftermath of neutron star collisions. These discoveries validated Einstein's predictions and solidified LIGO's place in scientific history, earning its researchers the 2017 Nobel Prize in Physics. Yet, these detections only scratch the surface of what gravitational waves can reveal. They provide insights into the fundamental nature of gravity, a force that permeates the universe yet remains profoundly mysterious. Gravitational waves demonstrate that gravity is not an instantaneous pull between objects, as Newton envisioned, but rather a field that can ripple and carry energy through spacetime. This means that changes in a gravitational field propagate at the speed of light. If the Sun were to vanish, Earth would continue orbiting for 8 minutes, the time it takes for the information to reach us. Such revelations align gravity with the other fundamental forces of nature, electromagnetism and the strong and weak nuclear forces, which also operate as fields with wave-like properties. Light, for instance, is a ripple in the electromagnetic field. By studying gravitational waves, scientists hope to uncover connections between gravity and these other forces, potentially leading to a unified theory of physics. One tantalizing possibility is the detection of primordial gravitational waves, ripples generated during the universe's earliest moments. Current cosmological models suggest that the universe underwent a period of rapid inflation shortly after the Big Bang, expanding exponentially in less than a fraction of a second. This inflation would have generated gravitational waves, encoding information about the universe's infancy. These primordial waves would have traveled through spacetime for 13.8 billion years, reaching us as faint whispers from the dawn of time. Detecting such waves is a formidable challenge. LIGO and its successors, like the European Space Agency's planned Laser Interferometer Space Antenna, LISA, are being designed to filter out the noise of more recent cosmic events. LISA, with its kilometer-scale arms positioned in space, aims to detect waves from the universe's earliest epochs, providing unprecedented insights into the nature of inflation and the origin of gravitational fields. The detection of primordial waves could confirm key assumptions about the universe's birth. For instance, gravitational waves could reveal whether inflation was a gradual process or a sudden, violent event. They could also shed light on the nature of the gravitational field itself. Unlike the Higgs field, which gives particles mass, gravity is linked to energy and momentum. This distinction means that gravity could have existed even before the Higgs field emerged, influencing the universe long before matter acquired mass. Indeed, most cosmologists believe that gravity emerged during the Planck epoch, the earliest phase of the universe, when spacetime was compressed to scales smaller than a proton. At such scales, the classical laws of physics break down, and quantum effects dominate. Understanding gravity in this regime requires uniting general relativity with quantum mechanics, a goal that has eluded physicists for decades. New theories, such as string theory and loop quantum gravity, offer tantalizing possibilities. These frameworks suggest that spacetime itself may have a discrete, quantized structure, and that gravity arises from fundamental vibrations or connections at this microscopic level. While these ideas remain speculative, they highlight the profound connections between gravity, the fabric of spacetime, and the origins of the cosmos. Leaving our dimension. Lisa Randall's journey through Yosemite offers a striking metaphor for the forces that govern our universe. As she climbed the sheer rock face, she grappled with gravity, a force so weak that a single rope could suspend her against its pull, yet so unyielding that it accelerated her descent with unforgiving precision when her grip faltered. This duality of gravity's weakness and persistence mirrors its enigmatic nature in physics, the least understood of the fundamental forces, yet essential in shaping the cosmos. At the heart of our struggle to comprehend gravity lies a profound incompatibility between the two pillars of modern physics. General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime, a framework that elegantly explains the behavior of massive objects and the large-scale structure of the universe. Quantum mechanics, on the other hand, delves into the subatomic realm, where particles and forces obey probabilistic rules that defy classical intuition. Despite their individual successes, these theories clash irreconcilably when applied together, particularly at the Planck scale, a realm so minuscule that the distinctions between space, time, and energy blur. Most forces in nature, such as electromagnetism and the strong and weak nuclear forces, have been successfully integrated into the quantum framework. Each is mediated by messenger particles, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. These particles arise from quantized fields that permeate the universe, their interactions governed by the elegant mathematics of quantum field theory. Gravity, however, remains the exception. Theoretical physicists have long posited the existence of a quantum particle called the graviton, a carrier of the gravitational force. Yet, detecting such a particle has proven elusive. The graviton's faint signal would require an impossibly large detector, one with a diameter surpassing that of our solar system, to measure its effects with precision. Complicating matters further, attempts to quantize gravity lead to mathematical divergences. When energy and momentum distort spacetime at quantum scales, the resulting feedback loop generates infinite energy densities that cannot be renormalized, a cornerstone technique used to tame infinities in other quantum fields. This failure suggests that our current frameworks are inadequate for describing gravity at the smallest scales. To address these challenges, physicists have proposed radical new theories. Loop quantum gravity reimagines spacetime not as a continuous fabric but as a network of discrete loops, each woven into a fine lattice at the Planck scale. This approach avoids the infinities that plague traditional models, treating gravity as an emergent property of spacetime geometry rather than a force in the classical sense. While promising, loop quantum gravity lacks the experimental evidence needed to confirm its validity. String theory offers another paradigm, envisioning the fundamental constituents of reality as tiny vibrating strings existing in a multidimensional space. In this framework, the three spatial dimensions and one temporal dimension we experience are merely emergent properties of a larger, more complex reality. String theory elegantly accommodates gravity, suggesting that its weakness arises from its connection to these hidden dimensions. Specifically, gravity's effects may be diluted as it propagates through additional spatial dimensions beyond our perception. Here, Lisa Randall's work enters the stage. Her groundbreaking theories extend the idea of multidimensional space, proposing that our universe is a three-dimensional brane embedded within a higher-dimensional bulk. In this model, the other fundamental forces are confined to our brane, while gravity resides primarily in a separate brane. The interactions we observe are merely the leakage of gravity from this gravibrane into our universe, explaining its apparent weakness. Randall and her collaborator Raman Sundram devised a mathematical framework to support this idea, showing that warped geometries in higher dimensional space could account for gravity's exponential decay across the bulk. This approach resolves the inconsistencies of supersymmetry, a theory that predicts partner particles for every known particle but struggles to align with observational data. By situating gravity in a separate brane, Randall and Sundram preserved the elegance of supersymmetry while reconciling it with reality. The implications of Randall's theories are profound. If gravity truly originates in another dimension, it may never be fully detectable within our own. The elusive gravitons sought by particle physicists might simply have an infinitesimal probability of straying into our universe, making their detection a matter of extraordinary luck. Yet, the tantalizing possibility of higher dimensions reshapes our understanding of the cosmos, offering a glimpse into realities beyond our own. Despite its elegance, Randall's work, like all theories of quantum gravity, remains speculative. The mathematical consistency of her models is compelling, but experimental validation is essential. Just as gravitational waves were once dismissed as theoretical curiosities until LIGO's groundbreaking detection, so too might these multidimensional theories await their moment of empirical vindication. To this end, physicists around the world are developing instruments and experiments to probe these possibilities. Particle accelerators, such as the Large Hadron Collider, continue to search for evidence of supersymmetry in extra dimensions. Meanwhile, gravitational wave observatories and next-generation detectors like the Laser Interferometer Space Antenna aim to uncover new insights into the nature of spacetime itself. As Randall's theories remind us, the universe is far more intricate than it appears. From the immensity of galactic structures to the subatomic dance of particles, every level of reality is interwoven with mysteries that challenge our intellect and imagination. Gravity, the silent architect of the cosmos, may hold the key to unlocking these secrets. Whether its origin lies within our universe or beyond it, the quest to understand gravity is a journey that transcends dimensions, inviting us to explore the very foundations of existence.